Good morning, ladies and gentlemen. Thank you for being here. My name is Michael Tran. This is James Taylor and Victor Ingles. We are Team 6, and we're doing the body cooling system. Our project is sponsored by Ronald Guerrero, who's here with us today. The design objective of our project is to design a lightweight wearable garment that can cool the human body. This is for the general audience public, to people who love doing outdoor recreational activities or work in hot environments where heat exhaustion and heat stroke are common. The initial laws and equations governing our system is based off laws of heat transfer and thermodynamics. There are four main variables in this calculations, which is energy rate, heat coefficient, active surface area, and temperature difference. Our system process is divided into four main stages, really. Conduction between the human skin to the materials of the system, convection from the materials to the coolant, convection again to the coolant to the cooling device, and finally a mix of convection and convection to a heat sink which will dissipate the excess heat. The human body. The human body is the body of interest. The average body temperature is about 37 degrees Celsius. Hyperthermia sets in around 40.6 degrees Celsius, giving us a maximum set of temperature difference of 3.6 degrees Celsius. As you see here in the thermal picture of an average adult, heat is concentrated in the upper torso region, which we will be aiming at, which is from the ribs to the shoulders. The reason for this is because most of our organs are active right there, which is the lungs and the heart. The body's natural response to a rapid cooling effect is called cold shock response. What happens is the body freezes up and our blood veins and arteries contract suddenly. Example of this happening is falling through a thin ice lake. This is something we're trying to avoid at all costs. For calculating the energy and energy rate we need to represent the workout, we're using Fourier's law of conduction and deriving that into a thermodynamics equation of changing internal energy. Based off data of the average human body, the average energy we need to extract from the body from hypothermia states is about 874 kilojoules. For our time generation, we're using 10 to 15 minutes due to the fact that people who are using these systems will be doing for exercising, having a 10-minute break in between sessions. With this, the estimated energy rate our system is working at is about 1.46 kilowatts. Now, I'll show it to my colleague, James, to talk about our cooling device in more in depth.
Hi, so I'm going to be going quickly over the components of our cooling device, and the main component out of the entire cooling device will be the Peltier device, which is a thermoelectric device that is a solid-state semiconductor-based electronic component. And it has the ability to transfer a voltage input into a temperature difference. This temperature difference separates a hot plate and a cold plate on the Peltier, allowing for heating or cooling. For our purposes, what we were doing is using this for cooling water throughout the system. In order to keep that cold plate cold, we must remove as much heat as possible from the hot side of the Peltier plate, and to do this we will be using a heat sink and fan. And so as far as cooling is concerned, we're going to be using a water block, a pump, and vinyl tubing to distribute and circulate water throughout the system. And the ideal situation will be for our system to run on completely operated on battery control. So here's a design schematic of our design. And essentially, as I alluded to before, this is the Peltier device. One side of it will be cold, one side of it will be hot. So as I mentioned before, we must remove as much heat from the hot side of the Peltier plate. So in order to do this, it will be directly connected to a heat sink, which will absorb heat from the hot side of the Peltier plate and will distribute it throughout the heat sink. And in order to disperse this heat energy, we will be using a DC-powered fan in order to disperse it out into the surrounding air. Now, as far as cooling is concerned, the cold side of the Peltier will be touching the water block. Well, the water block will get chilled by the Peltier, and water will be circulating through it in a closed loop of vinyl tubing through the inlet and outlets of the water block, as you see here, into a submersible pump, which will be inlets and outlets here. And in this video, we were just testing we did our first test of our Peltier plate, and we can see in this video that by using the thermometer, we can actually see that we are getting a drastic decrease in temperature at a very fast rate. And now Victor will be going over our alternate designs.
Thank you, James. All right, so for our alternate designs, the one thing we wanted to focus on was the orientation of the tubing. So as you can see by the design number 1, we want to have some sort of like a coil-like orientation with 180-degree bends. Now, the benefits to this design is that it will be very flexible. We have evenly distributed cooling in the front, as you can see by this picture, and it allows a zipper in our vest. So what we're trying to do is have something that could be easily taken off, put on and taken off. However, with this design, as you can see in the bottom left schematic, the back area is very exposed and has little amount of cooling delivered. So for our alternate design number 2 is a very simple design, something like an X formation. So the benefit for this is that we have maximum flexibility because there's not as much tubing in the way. And minimal, as you can see, there's very little tubing required, so that minimizes our cost overall. However, though, as you can see by both schematics, not much of the body is being cooled, which is a huge design factor. And for our third design is a design where the tubing wraps around the body horizontally, as you can see by both schematics. The benefit to this one is we get the maximum amount of cooling to the body, which is very important. And even it's both front and back has evenly distributed amount of cooling. However, as you can see by the schematics, there's a lot of tubing required, so the overall cost of the design goes up. And we have limited flexibility in the design of the vest itself. For our related standards, we found some standards already where ISO gives us some standards related to the refrigeration system, testing, manufacturing, things like that. It also provides a standard about human health. Human health is very important in our project because we're dealing with a system that's meant to cool the body. So we have to design it in a way that, as Mike said earlier, we don't risk putting the user into the rapid cooling shock. And we plan to meet up with professionals on campus and through other sources to get do some more research on what exactly is safe for the body. ASTM provided us with some standards relating to the vinyl tubing that we plan to be using, some standards on the design, how we can use it, and ANSI provided us with standards related to the battery pack in terms of maximum operational voltage and basically the design of the battery pack itself so that it's safe for the consumer. So for our global design, one thing we want to focus on is the instruction manual, which is going to be a combination of both pictures and multilingual statements. So the reason for this is to accommodate, because our audience is the public worldwide, so we want to accommodate for those of different languages, so we have to make a multilingual instruction manual. Also, the materials that we use in this design, we want to design it in a way that the materials are readily available across the world so that we don't limit production in a specific area. If we cannot come up with a universal design, we will provide alternatives to match the needs of other nations. If time permits, because this is the vest we're trying to sell for the consumer to buy, we want to add some customizable options so that when you buy the vest, you could shape it in the way that you want to give yourself a sense of individuality when wearing this device. Flexibility is a huge thing. This is a vest that we want lightweight, portable, and that you just slip on, you turn on, delivers cooling to the body. So flexibility is a huge design criteria because around the world there's people of various masses and size. And because we want to sell this, to give it to the public, maintenance is very crucial. We want to provide it in a way that's easy for anybody to change anything they need without having to go to like a specific shop or something. This is a chart of the breakdown of the timeline of our project. As of today, we are on pace with this project. Over the summer, we want to, finalize the design, start simulations, and eventually have a prototype ready by the end of the summer so we can start doing actual testing. This table just provides a division of responsibilities for each of the team members. This is not set in stone; it's just a general table, but we just, to provide. And yeah, thank you for listening to our presentation. Any more questions? Or is there any questions? Sorry.
Okay, I noticed that you designed around the max cooling rate. And the question I'm asking is there going to be a temperature feedback loop on the systems, for example, because not only is cooling important, but when you've got a chilling system, heating up is probably just as important to ensure that you don't freeze the person.
Or we put inside is a voltage regulator to control the voltage. While you're controlling the voltage, you control the temperature of the peltier plate. So you can get to a certain amount of temperature, you can cool the body within the 10 minutes, and then it will just turn off by itself. The kind of power.
Yeah, we want to avoid, any sort of people get some curiosity, say, oh, how far can I push this to its limit? We won't be able to do that because of a voltage regulator we plan to put in there. So that the max you could do is the targeted, in case, let's say we're trying to cure someone from hypothermia, so you want to have, that's the maximum, but for most general applications, you won't need to go as that high temperature difference.
Okay, so it's going to have a thermal limiting capability. The other question I wanted to ask you is on your tubing. Is it going to be incompressible? Is it going to? My concern is that someone sits in a chair, or somebody lays down, and they collapse the tubing. And what would that influence be?
Well, the vinyl tubing is actually very flexible. So, say for example, somebody were to slip and fall and stumble on it, like you said, it's not necessarily the easiest thing to puncture. Is it possible to puncture? Yes. However, it is resistant enough and flexible enough to where it could probably take quite a bit of pressure before having a rupture.
My question is really more, he's laying down. Now all of a sudden, all the tubing that you've got on the back of him is pinched.
Yeah. The way we thought about design was more of just like, let's say you're taking a break, maybe you're standing up chatting with some friends, you pop it on, turn it on, or if you just finish, doing something like outside in heat or something. We assumed standing, but these are more things we have to think about, as you said, about sitting down, things that we'll think about. We just assume for now as a frame of reference, just standing up and just popping it on and turning it on.
Okay, thank you.
Questions?
How much research was done into systems that may not be as individually or all-encompassing as this design, but for example, motor racing? NASCAR, as a classic example, has a central distribution center, but it's a liquid-cooled suit. So how much research did you guys look into in terms of especially optimization of the tubing paths?
Mostly from our Gaussian equation of heat transfer, how pretty much two main variables is heat coefficient and surface area. Those are essentially like a set temperature and a set heat rate. Those need to be varying pretty much. Heat coefficient changes based on the material you use. That includes the clothing, the tubing, and the mesh underneath. As for surface area, it's pretty much the orientation of our tubing itself. Based off the numbers we have, for example, like the numbers we have right now is going to be varying because of the body masses, and also we have to take into consideration the body's natural ability to get rid of heat, which is through radiation, natural convection, and sweating. And based off the equation of let's see, where is it? Here. Based off our heat equation here, we're going to be using, it will change all along the way. Pretty much, if we use less surface area, we find a material that's very heat coefficient, high heat coefficient, make it more flexible. If not, we want to aim for a body cooling temperature for because of a high CT. We might have to do a higher surface area for even cooling, prevent pretty much cold shock response, and pretty much find a lower material rate.
Any comments?
The
question?
go ahead.
Yeah, go ahead.
Would the user be adding liquid into the suit, or would that just be one time and that's it?
So the way this was designed, could you just pull up the schematic for me, please? So the way that this was designed was specifically like easy maintenance. So The idea of the submersible pump, this pump right here, the idea of the submersible pump is that it will be one closed loop between it and the water block that you see at the top. So when you want to, let's say, refill water or take out water from your system, it's as easy as putting that pump into a sink or somewhere where you can have a large container where you can submerge the pump into it. And what the whole purpose of it is to make it easy for the user to fill and disperse their water as they see fit. So let's say, for example, they didn't use a biocide, for example, through their tubing, and it gets, algae or something. We wanted to make it easy for them to be able to replace that water that travels along in that tubing.
And also, another comment. The titles in your presentation, they're a little bit hard to read because of they're white against the blue.
The contrast
Yeah.
is off.
Contrast is almost minimal.
For the next presentation.
Okay, thank you.
Sorry about that.
Light blue, white on light blue.
Yeah, a couple of things. First of all, the costs. I mean, how much is it going to cost to produce such a
Well,
system?
luckily, with our system, the majority of the components are pretty widely available, and each component individually are pretty cheap. We haven't done a full cost analysis of the entire system when it's completely finished. However, we are running at a budget of, our target price point will be underneath $200. That way, we want to get into a consumer market where, if we set the price point too high, they're not being scared away. We want something that's affordable and available throughout the world.
Now, also you said in your presentation that you're going to seek out professionals on campus.
On the main campus, in terms of the human health, to make sure that we don't.
So which professionals? Like who?
Those who PhD in the medical field, in the medical field, just we want to get as much sources as we can in terms of like what's allowed to be pulled, at what rate, what is something to avoid. So we have many resources on campus, the whole medical department. If not, we can consult other professionals, via email or calling. So it's a lot of sources we can use. But we met the main campus, the medical department over there.
That it? Yeah, go ahead. Yeah, please.
On the, you showed two concepts. One has a short vest type of look, and the other one was looks like a bigger, bulkier type of vest.
Right.
Were those going to be? I didn't see any specs on it. Weight and size. Will it be bulky that you can't wear underneath your clothes, or would it be something that you could wear underneath your clothing?
The idea would be primarily to wear it over the clothing, but we also wanted to be able to touch the bare skin as well. So like the ideal, and also we're also making the system adjustable. So say for example, like you're wearing bulky clothes, like let's say you're a construction worker outside in hot temperatures. We wanted to be able to either basically adjust to the person. So whether or not they want to wear it over their clothes or whether or not they want to wear it inside within their clothes on top of their body should be their option completely. So we're looking to try to make both readily available.
What about perspiration?
Perspiration?
Yeah. I mean, because you're going to have to wash whatever, so if you're having it inside your clothing.
Okay, so you're talking in terms of condensation.
Right.
So the idea,
Sweat.
sweat,
Sweat.
just more sweat. Okay, so the idea behind is it sweat or condensation? I don't know.
It
Sweat.
can be both.
Okay,
Sweat
so
is.
in regards to
Right.
condensation, then I'll answer that question. In regards to condensation, two reasons why condensation is our biggest enemy. And number one being that it would, too much freezing of the Peltier plate could drastically reduce its efficiency and also completely destroy it over time. And number two is onto your point, we do not want to make a system in which when people wear it, all of a sudden they're getting wet due to the condensation. So the idea behind it is to not lower the water temperature down so low that the ambient air around it, the moisture will not slow down and build up on top of that. on top of that tubing. So that way, you know, you wear it, it's dry all the time, and you never have to worry about
Okay, so that's.
wetting yourself. Because, yeah, it'd be highly uncomfortable. Right.
Hey, stop that. All right, so construction workers that are using that over their clothing, there'll be no,
The idea is to not let them wet.
Have more moisture than there already is, basically.
not let them get too condensed?
Yes,
Or
yes.
condensed, whatever.
For lack of a better word, yeah.
All right. Like he said, it looks really bulky. So let's say you want to wear it underneath your clothing.
Right.
Will there be a better design that's not so bulky?
That's something that, for the fall, when we actually get into the manufacturing of the vest itself and the choice of materials, that's where our limitations are going to be in terms of how thick it needs to be, or just how, because we also don't want to insulate the tubing as
Right,
well.
right.
So that's all going to be based upon the materials and components that the finished product will use.
And the finished product also includes women's forms and stuff?
Absolutely, yes, absolutely. This is supposed to be designed, we want to accommodate people of all shapes and sizes. So, yes.
Okay.
This came up actually in previous meetings with Ronald. We were, having meetings. And the idea is really to make it a little bit, trendy for young people, sports people, really to put it on and, feel good about it. Exactly. So we did talk about it, but because they're so early in stages of design, they didn't pay attention to that part yet.
Right.
So we're just trying to figure out the basics first, and then we will try to make it more acceptable and, because it's very important, obviously.
Yes.